Hello everyone, so my name is Sam Dow, and the topic of my presentation today will be on using the equivalent circuit approach to develop electrochemical batteries in MapleSim. So there are, as you know, there are two distinct approaches to modeling batteries. One is so the first approach is based on the electrochemical fundamentals, the fundamentals of electrochemistry to describe the behaviors of batteries. For example, we can use partial differential equation to describe the mass transport of the lithium ion across the two electrodes based on the electrochemical approach. But this is not the approach that we're going to be talking about today. So the approach that we're going to be talking about today is going to be, as you can see here, we're going to be using the electrical components to describe the behavior of an electrochemical cell. So this is a typical representation of a battery based on an electrical equivalent circuit approach. So you can see that there's a bunch of RC circuits and a series resistors. So I'm going to get into details about this model in a moment. So the ultimate goal of modeling a battery using the equivalent circuit approach is we're going to need to find a way to describe the battery voltage curve based on some of the inputs, for example, the open circuit voltage and the voltage drops across the resistors and the RC circuits. And also we need to describe the battery voltage as a function of the state of charge, and if we have to model the battery voltage for a stack, we don't need to describe the voltage as a function of the number of cells in the stack as well. And one of the most important aspects of modeling a battery is that we need to describe the transient response when we switch the current. For example, here. So this plot shows comparison between the two cases. One is the battery voltage curve when we don't have any transient response, and the blue curve is corresponding to the battery voltage curve when we have a transient response. So you can see that without transient, the battery voltage curve will change to the open circuit voltage value instantaneously when we turn off the current. So this curve can be obtained by applying a power current on the two terminals of the battery. So with the transient response, you can see that there is a smooth transition from one voltage value to another value when we switch the current. So this is something that we need to capture in our battery model as well. So the presentation today will be entirely in MapleSim. So I'm going to be jumping to MapleSim in a moment. So for those who don't know what MapleSim is a physical modeling tool which was built on the foundation of the symbolic computation technology of Maple. So it can the symbolic engines Maple allows MapleSim to handle the complex mathematics in the engineering models, and it's also allows MapleSim to handle multi-domain system. For example, in one single model, you can have components from electrical domain, mechanical domain, hydraulic domain in one single model and simulate all of them together. So let me go to MapleSim now. So what you see on the screen right now is MapleSim. So on the canvas in the middle of the screen, you can see that this is a typical representation of an electrochemical cell based on equivalent circuit approach. So there are two different linear circuits. One is on the left hand side and the other one is on the right hand side. So the linear circuit on the left hand side allows you to model the battery capacity. So you can see that we have a very large capacitor here, and the value of this capacitor, I set the value of this capacitor to 3600 farad. So it means that if we apply a 1 amp current across the two terminals of this capacitor, it will be completely discharged in 1 hour. So the value of the capacitors that I'm using here is equivalent to an 1 amp hour capacity for a battery. So we can use this to define the capacity for a battery. If we want to double the capacity of the battery, for example, if we want to increase the capacity of the battery to 2 amp hour, you can just simply double the value of this capacitor. So I'm using a signal current block in MapleSim here so that I can discharge the capacitor by using the same currents that I'm using to discharge the other side of the other linear circuit on the right hand side. And I also, as you might have noticed, I also set the initial voltage across this capacitor to 1. When we apply a discharge current across this capacitor, the voltage across the capacitor will drop from 1 to 0, since that is corresponding to the state of charge of the battery going from 100% to 0%. Okay, so by using a voltage sensor to measure the voltage across the two terminals of this capacitor, we can use this to represent the state of charge of the battery. So now let's talk about the linear circuit on the right hand side. So the linear circuit on the right hand side is consists of a series resistor and 2 RC circuits. Okay, so the purpose of this resistor here allows us to model the voltage drop across the battery, and the 2 capacitor here allows us to model the transient response that I just mentioned about on my PowerPoint slide. And the only connection between the this linear circuit on the right hand side and the left hand side is through the block in the middle here. So I'm just using a gain, which basically tells MapleSim to apply a voltage on the circuit on the right hand side based on the value of the state of charge of the circuit on the left hand side. So basically what I'm doing here, I'm just trying to describe what I call the open circuit voltage equation for the equivalent circuit battery. So the open circuit voltage in this case is really simple. It's just this is 4 times the state of charge of the battery, and I just apply that voltage directly on the circuit on the right hand side. So in order to run the simulation, you can first need to set the simulation time. So here I'm using 1 hour simulation time, and you can also add a terminate block in MapleSim to terminate the simulation, to make sure that the battery is not over discharged, and end the simulation when the state of charge drop to a certain value, for example. So it's using a less threshold component in MapleSim, and I will connect that to the output of the voltage sensor, which means the state of charge of the battery. And if the state of charge drop below 0.01, which is 1%, then I will terminate the simulation, and I will output a message, for example, battery over discharge. Okay, so now if I run a simulation, I can set the simulation time to, for example, 2 hours, and it won't. So depending on the value of the state of charge, the simulation might be halted before that. So now, in order to run the simulation, I simply click on the triangle button at the top. Now I have 2 probes attached to the circuit. One attached to the linear circuit on the right hand side, and one attached to the gain, which allows me to measure the value of the open circuit voltage. So the probe here allows me to to plot the voltage and the current on the battery. So now the simulation is completed. I'm using a pulse current to discharge the battery. So the value of the pulse current is 1 amp. So basically the amplitude of the current is 1 amp. So basically I'm just turning on and turning off the current based on the parameter for the pulse signal, the input signal that I'm defining here. So the period for 1 pulse is 600 seconds, and the width of the pulse is 80% of 600 seconds. So you can see that in the simulation result after you run the simulation. So let me make the plot a little bit bigger. So this is the pulse current. So you can see that I just discharge it by a pulse current. I turn on and turn off the current. So the current value switch from 1 amp to 0 amp until the battery is completely discharged. The second plot shows the battery voltage. In this case, this is a linear curve. And you can also see the transient response here as well. If you just zoom in this area, you can see the battery voltage smoothly move from one value to another value. So there's some transition between them instead of instantaneously increase to the open circuit voltage value. And the third plot shows the state of charge of the battery. I'm sorry, it's the open circuit voltage of the battery. So now, if you want to, you can also observe the effect of the transient response when you, for example, when you disable the capacitors in the motor. And let's see if we do this, and what's going to happen if I just simply disable these two capacitors here. If I run the simulation again, you're going to see that in the voltage curve, which is the second curve, the battery voltage increase, rise and drops instantaneously when you change the value of the current. So the two capacitors that I'm using for this model are different. So one has a value higher than the other. So when the current is applied on the two terminals of the battery, these two capacitors will be charged up, and when the current is turned off, the two capacitors here will be discharged. So the value of the first capacitor is 5,000 farad, and I call it the long time transient because it takes a longer time for it to be completely discharged. And the value for the second capacitor is 700 farad, and I call it a short time transient. So now this is a very simple open circuit battery. It's open circuit. This equivalent circuit battery model. In order to you can also use some equation, some expression to describe the nonlinear relationship between the battery state of charge and the open circuit voltage. And you can do that using the MapleSim custom component. So let me delete the gain block in the model for now, and let's use some nonlinear equation to describe the relation between the battery's open circuit voltage and battery state of charge. So I just select the custom component worksheet in MapleSim, and I will be using that to describe the nonlinear relationship. So I call it the open circuit voltage equation. Okay. So now we are in Maple environment. So this is a special, a predefined Maple template that allows you to define your own equation and then bring that into MapleSim. So what I want to do here, I want to define the open circuit voltage equation. Let me make the font size a little bit larger so you can see it better. So VOC, which is the open circuit voltage. And I want it to be a function of, so N cells, that's the number of cells, times just want to define an arbitrary nonlinear function here. So that's a parabolic curve plus so this is what I want to define. So the open circuit voltage is given by this parabolic function times the number of cells. And if I click on refresh all, this worksheet will be able to identify what parameters we're using in the model and how many variables are in the equation. So you can see that there's this one parameter which is called n cell, and we can give it a description. Just we call it the number of cell in the stack. And we have two variables which are all function of times, the state of charge and the open circuit voltage. So now we need to define the input and output port of the custom component as well. So I want to add two ports, one for the input, and I'm gonna use a real signal, and I call it and this is the state of charge in, and I want to assign it to the state of charge variable. And the second port is what I'm going to be using for the output. So it's also a real signal, but I want to use output. So B out, and that would be our open circuit voltage. Okay, so after that, I simply give it a name. So I just leave it the name as it's using the default name for the component. And then after that, I simply click on generate MapleSim component, and at the same time, it will generate the MapleSim component for the open circuit voltage. And at the same time, the worksheet also generates the Modelica code for the custom component as well. So if you are interested in using the Modelica code and familiar with that, you can reuse this Modelica code and then use that in any software that supports Modelica. So now I have my open circuit voltage block, which would use a nonlinear function to relate the battery state of charge from the circuit on the left hand side to the open circuit voltage block on the right hand side. So now I have a nonlinear. So now the two linear circuits are connected nonlinearly through this custom component block. And when I select the component, you can also realize that it has one parameter, which is the number of cells that we just defined. So if you want to so right now we only have one cell in the stack, but if you want the stack to have 10 cells, for example, we can simply enter 10 in this parameter block. So now if we run the simulation now, and let's see what's going to happen. Okay, so this is our nonlinear. So this is our nonlinear voltage. Okay, you can. It looks like that the peaks a little bit high because of the value of the resistors are a little bit high. We can simply reduce them. It's just the value of the resistor here just to make them look more reasonable. Let's see this. That's 10 milliohm for this, and make it 20 milliohms for the series resistor, and we run the simulation again. So now you can see that it looks much more reasonable. That's it a little bit. So so the plot on the left hand side is still our power discharge current, and the curve on the right hand side shows the voltage of the battery going from close to 4 volt to below 3.5 volt when the state of charge go from 100% to 0%. Okay. So this is a very simple model in which we only use constant values for the resistors and capacitor. So in reality, the value of these resistors and capacitors are also the function of the battery state of charge as well, and this function is usually nonlinear. Okay, so so that's why we need usually to use a more sophisticated function to describe the nonlinear relationship between the state of charge and the value of not only for the open circuit voltage but also for the RC resistors and capacitors as well. And this is what we're going to be seeing on the second model that I'm showing here. So the model that I'm showing here is very similar to the previous model, except that if you step inside this block, you're going to be able to see this the circuit for the mod inside has a very similar structure. So we have a linear circuit on the left hand side, and the second linear circuit on the right hand side, and the relationship between the value of the variable resistors and the variable capacitor here are determined by this custom component. So the custom component here has one input, which is still the state of charge of the battery, which is measured by using a voltage sensor across the two terminals of the capacitor from the circuit on the left hand side. So let me so let's say the question is how would we determine the open circuit voltage for a model like this, for a model like this, so that is able to capture the behavior similar to a real battery. So so normally we'll be using the experiment data. We need to measure the open circuit voltage from a real battery, and then we're going to be using that to we're going to be using the curvating capability in Maple in order to identify the functions that we're going to be putting in this custom component. So let's say we have a data that looks like this. So this is an Excel spreadsheet that has a set of data. So there are two columns. The first column is the battery state of charge, and the second column is the open circuit voltage of the battery. So the second voltage of the battery is given by the battery state of charge, and it's described by this table. So we can either use this table directly in the MapleSim model using the lookup table, or you can use the curvating capability in Maple to describe the open circuit voltage of the battery as a function of the state of charge using a smooth function. So let's go back to the model here. So I have predefined a Maple worksheet that allows you to curve it the open circuit voltage data that you have seen. So this is the Maple worksheet, and this worksheet is attached to the model. So when we open up this Maple worksheet, you can see that the model diagram will show up at the top, which indicates that the worksheet is connected to the MapleSim model. So you can simply run the restart command in Maple to clear out the memory that you might have from the previous calculation. And we're going to be using some of the API commands. For example, the link model command allows me to link the variable named A to the MapleSim model. And the next step, I will be using the get attachment command in Maple to read in the open circuit voltage data in the Excel file. So when after execute this command, this is what you're gonna be seeing. So if you double click on the matrix here, so this is a table which is identical to what we have seen from the Excel spreadsheet. So the first column is state of charge, and the second column is our open circuit voltage. So now we need to define the form of the nonlinear functions that we want to curve it. So this is my my first estimate of the nonlinear functions that I will be using. So this is normally a typical kind of functions that we usually use to describe the voltage curves of the battery. So it's a combination of an exponential function and a polynomial. So you simply execute this command so that it's going to be able to print out the general form for the function. So now we need to determine the parameter p1 through p10 for this smooth function. And for curve fitting, we're going to be using the nonlinear fit function in Maple. We're gonna pass into this function the its generic form of the function and the data set that we just read in from the Excel. And the variables that we want to be curve fitting is going to be state of charge. So I simply execute that, and this is the final form of the function that we're going to be using in the custom component block. You can also plot this function and compare that with the experiment data. So you can see that this is a very accurate curve fitting. So the two curves are almost completely overlapping on top of each other. So I simply copy this function and put that into the custom component block that we see here. So I just double click on that, and this is the functions that users saw in the other Maple worksheet. Okay, so this open circuit voltage is given by n. So in this case, n is the number of cells in the stack, and this is in the open circuit voltage equation as a function of the state of charge. I can also go ahead and then define the equation for the series resistor, for the series resistor and the two resistors in the RC circuit, as well as the equation for the long time transient and the short time transient capacitors in the two RC circuits as well. So they're all given by a function which is a combination of an exponential function and a polynomial. So you can make this function bigger if you want. Okay, so I parameterize this function so that I'm able to adjust the value for the function from the MapleSim GUI. So since this is a predefined model, so this component has been compiled to a MapleSim component. So you can see that it has one input, which is a state of charge, and the output are the open circuit voltage, and the output for the 3 resistors and the 2 capacitors for the RC for the RC circuits. And once you generate the MapleSim component, this worksheet also generates the Modelica code so that can be reused as well. So now let's go back to the MapleSim model. Okay, so now because this custom component has been parameterized, once you compile that, you're going to be able to see all the parameter for the custom component in the column on the right hand side, and you can also see the parameter n, which is the number of cells in the stack as well. So the next question is that how would we determine the value of these parameters? So that is an interesting question that we usually encounter, from my clients. One way to do that is that you can manually adjust the value of those parameters until you have a reasonable response. And the second way is that if you have the experiment data for the battery, you can use that to identify the parameters, as you see from this parameter block here, by using the parameter ID tool that we have in MapleSim. So this is the parameter identification tool that I'm talking about. So let me just open it up. Okay, it's a little bit lacking. So this is the Maple worksheet for identifying the battery parameters. As you can see that this Maple template is attached to the model. So once you open it up, you're going to see the model diagram at the top as well. So this parameter identification template allows you to connect to the MapleSim model and pull in the two set of the battery measurement data into the worksheet and use them for identifying the battery parameters. So I have two set of data that I'm using here. So one for the charge process and one for discharge process. So the charge process is so when you read in the set of parameter, Maple will plot the curves corresponding to the data set as well. So the red curve is corresponding to the the discharge process, and the green curve is corresponding to the charge process. And the current that I'm using for both curves here have the similar value, except that they have different size. So one is 6.6 and the other one is 6.6 minus 6.6. Okay, and the next step is to select what parameter you want to identify. So there are 21 parameters that you can identify in the model, so including the capacity, that will be 22 parameters. So so once you load up the MapleSim model, it's gonna be able to identify how many parameters the model has. And from this drop-down menu, you can select what parameter you want to identify. So the capacity is one of the most important parameter, because it defines how long you can charge and discharge a cell. And the other parameter, you can select all of them if you want to. And this is a pre-run parameter identification result. Because of the limited time frame, I'm not able to run this on the fly. So the results here shows that so a very accurate curve fitting result. And at the bottom, you're going to be able to see the parameters that have been identified on the model. And you can simply click on this button, apply the MapleSim model to write the parameters back into the MapleSim model. So these are the parameters that have been identified. Okay. So now you already you have defined the open circuit voltage equation based on the open circuit voltage data, and you have also identified the parameter of the battery based on two set of experiment data as well. So the next step is simply you just need to define the simulation time, the solver that you want to use, and apply a charge or discharge current onto the model. You can use the charge current. You can also define an initial state of charge if you want to. If you want to charge that up from 0 to 100%, you can set the initial state of charge to 0, and the value of the current would be that would be applied on the model can be defined through this step signal. So now let me run the simulation. So this is the simulation result. So it sees that let me make it a little bit larger. So this is the discharge current, and this is the voltage of the battery. And the third plot shows the state of charge of the battery going from 100% to 0%. So now if you want to increase the number of cells in the stack to, for example, to 10 cells, you can simply enter 10 for the parameter n, and you can run the simulation again. Okay, so now you can see that the maximum voltage for the battery after the simulation goes up to 41 volts, so indicating that we have 10 cells in the battery stack. You can also use a pulse current that similar as in the other model, and put that into as a simply copy that pulse current, and I use that to discharge this battery pack. So I disable this block and use a pulse current to discharge it instead. So now if you run the simulation again, you're going to be able to see the behavior of the voltage curve when we charge and discharge the battery pack. Okay, so so the clear advantage of developing the battery model in MapleSim is that you can, so besides applying a voltage, a current or voltage profile to the battery pack, and investigate the behavior of it, you can also make it part of a bigger model. For example, you can include this battery component here, or a stack in a complete hybrid electric vehicle model. For example, in this model. So the battery packs that we see in the middle here is based on the equivalent circuit voltage for a nickel metal hydride battery, and it also has a power control unit. It has some of the motor components that allows the vehicle to recharge the battery by using the power from the internal combustion engine or from the regenerative braking behavior of the vehicle when the vehicle slows down. You can also model the thermal of the battery as well, and as well as using the thermal component in MapleSim to model the cooling circuit. So you can also use a real drive cycle. For example, this vehicle model is based on an FTP drive cycle, and I'm using a PID controller here to control the vehicle speed based on the FTP drive cycle at the input. And after that, you just need to set the simulation time, define the parameter for the model, and then run the simulation. So the simulation will take a little bit of time because this is a fairly large model. So this model describes the series hybrid electric vehicle. You can also define your own. You can also create your own hybrid electric vehicle configuration based on the knowledge as well. So when the green bar starts moving, that's when the integrator is solving the equations in the model. So after you run the simulation, you can see the temperature across the internal combustion engine, the battery pack, the heat flow. You can also see the speed of the vehicle while it follows the drive cycle, the fuel consumption, the battery voltage. So for example, here you can see that the red curve is the voltage of the battery pack. So it's going up and down because the battery is discharged and charged while the vehicle is doing the operation of the vehicle. You can also plot the engine power, tire forces, and other parameters as well.